Okay.
All right, looks like we're good. I'll go ahead and get started. On time. So just make sure those sheets that are being passed around that everybody signs them, because it's also the sign-in sheet for this session. So start off with, why do we lime in the first place? What are the benefits of lime? Number one, it neutralizes acidity. But one of the main goals of neutralizing acidity is actually to reduce the toxicity of aluminum and manganese. As a side benefit, it adds calcium and magnesium. It also, something that's not always talked about, it improves soil biology, which is great for nutrient cycling, and it improves pesticide efficacy, which means the efficiency of the pesticide. To start off with, make sure you understand what pH is, because sometimes we can overlook this. Pure water, when you split H2O, it's hydrogen and hydroxyl. Any addition of H makes it acidic. Any addition of OH makes it basic. So pure water is equal concentrations of hydrogen and hydroxyl. Actual rainwater has a pH that's lower than this because carbon dioxide gets into the water and creates carbonic acid and makes it more acidic. But pure water with no ions in it has a pH of 7. The P itself stands for negative log, because we had to put the concentration, it's the concentration of hydrogen is the negative log scale, because we had to put it on a scale we could read. What the log is able to do is take things that are very far apart and put them in a graph that you can read easily. So when you go from a pH of 4 to pH to 5, you're actually decreasing the hydrogen concentration by a times of 10. So that's what a log-based 10 scale is. So that's all pH is. It's the hydrogen concentration on a log scale. Comparing soil pH to some of the chemicals and things we might use every day helps you get an idea of what we're dealing with. That red region right there, that's most of the soils on the East Coast, the humid region. Calcareous soils, if you were over in the limestone valleys, you can have calcareous soils, which would be similar to the pH of baking soda. Sodic soils, maybe more out in desert areas, would be similar to milk of magnesium or antacid tablets. But we're mostly dealing with humid region, arable soils that have a pH similar to natural rain. Remember I said rain has slightly lower pH. So it makes sense that our soils, for one, would have a pH of rainwater, because whatever the pH it's being washed in is going to be the pH of the soil. So if for some reason rain started becoming alkaline or basic, then it would slowly increase the pH. Just like acid rain, say 30 years ago, was decreasing the pH of the soils because we were washing the soil, say, with an acid. And you could also end up dealing with forest soils, organic acids, maybe a little lower pH. And if you've ever dealt with mine waste, you wouldn't have acid sulfate soils. But for most cases, we deal with soils in this region from about 5 to 7. For agronomic reasons, and also we're on the East Coast, and it's mainly what the pH of our soils are naturally going to be. What causes acidity in soils? Hydrogen, of course, is the acid we're measuring, but aluminum can cause acidity. Aluminum itself hydrolyzes water, it splits water. So when it splits it, it creates hydrogen. It creates the acid. The hydroxyls from splitting water are often associated with the aluminum. But by splitting water, it creates acid. Iron, to a small extent, can also create acidity, not as much as aluminum. With calcium, magnesium, potassium, and sodium, all the things we call the base cations, they don't split water, so they don't produce acidity, and that's why we call them basic. So some soils are naturally going to be more acidic. A lot of it's due to weather. So over here on the East Coast, we have plenty of rainfalls, we have plenty of leaching. So all those base cations over time, if they're in the soil, leach out. And it leaves you with a lot of aluminum and iron. The aluminum iron, obviously, so they cause acidity. So minerals break down and release aluminum as they weather. So older weathered soils leach out the nutrients, release more aluminum, so they're naturally going to be more acidic. Soils in cooler climates, where you actually, if you go out to the desert, you have more evaporation. Evaporation brings salts to the surface, so you have a more basic pH. So some soils are naturally going to be more acidic. When you look across the United States, here's a map of precipitation and a map of soil types. You see the humid east here, with all this rainfall, and you can see that soil types follow. As you go out towards the desert, in these dry climates, you have specific soil types, aridosols, dry soils, and we have highly weathered, this orange here are ultisols, highly weathered ultisol soils in the east. But you also see some different patterns through here, and that's something else besides precipitation leaching out cations. You have to deal with parent material. What did your soil form in? So if your soil formed out here, and maybe you're in a limestone valley, you might have a more basic soil because it's getting calcium ions, say, from the limestone. But if you're in a sandstone soil, you might not have as many ions, and it might be a little more acidic. Piedmont in here has bedrock. These can be very old weathered soils, but that bedrock can also replenish nutrients over time. These coastal sediments that we live on over here, these sediments can be highly weathered, and most of the nutrients might have been carried out to sea as they were deposited. So it's not just the leaching, but what did your soils form in that are going to control the initial acidity that it has, or its ability to replace bases. Man also contributes. Additions of fertilizer can add acid to soil, like ammonium. Certain types of manure, organic acids from manure can also add acidity. And then you also have to think about the harvest. Obviously, if you don't add nutrients back to your soil, you're not going to be able to grow anything the next year. But as you pull those crops off, you're pulling nutrients out, you're pulling out bases. So you're actually contributing to this slow acidification of the soil if you never replace those nutrients. But if you didn't, you couldn't keep growing crops. So why do soil tests have two pHs then? The pH of the soil measures acidity. You can have one pH and then also a buffer pH on all these soil tests. And what does it tell you? Well, the pH, they typically just call pH, is the active acidity. It's the acidity that everything sees in your soil. It's the equilibrium point of your soil, which means all the biology in your soil, all the crops, they all see that pH of 5.9. It tells you the availability of the micronutrients and what's going on. The buffer pH lets you know what is held in reserve. What acidity is being held back in that soil, so that if you lime it, there's additional acidity being held back that can be released to keep that soil in equilibrium. And that's why we call it a buffer, because it buffers your soil from a rapid change in pH. So you think of it like an army. The active, this pH is measured typically in water. It's telling you this is what's going on right now. So on a battlefield, that's who would be fighting at that moment. But what's held in reserve back on the soil can replace that acidity. So if you lime it, that acidity comes off and replaces it. We call this the buffer capacity of the soil. Obviously, soils vary in their characteristics. Some soils have a larger buffer capacity than others. It can usually be tied pretty easily to texture. So buffering slows the rapid pH change, which is good for a soil because you don't want the pH to change rapidly. Say if we had acid rain or a lime soil, you don't want it to rapidly change because your crop's going to like a specific pH range. The biology is going to like a specific pH range. So the well buffered a soil is, it might slowly change. It might require more lime added, but it also means in the reverse, when it comes back, it acidifies slowly. So it's good to have a well-buffered soil. It might cost more to lime it, but it also helps you in the end in how quickly it acidifies. So that slow change also applies to how fast it becomes acidic. So why do we need to know the buffer pH? Soil acidity is more complex than just taking the water pH. That active acidity, it's measured by the water pH. It does let you know that's what your crops see, and that's very important, so you know whether you want to raise it or not. But soils have that acidity held in reserve. So here, this hydrogen out here is active. That's what that pH meter reads in the soil water. But you have some in reserve, so if you try to get rid of this acidity to reach equilibrium, this hydrogen might come off, or this aluminum might come off of the soil. So it's mainly exchangeable acidity that we're concerned with, acidity that can exchange on and off the soil. It includes aluminum, hydrogen, and sometimes iron. And it creates this need to know the buffer pH. That's the only reason we want to know, because we're going to lime these soils and increase how much lime you have to add. CEC for us is going to help explain most of the reserve acidity. Soils have a negative charge, for the most part, clay and organic matter. Most of our soil nutrients, calcium, magnesium, potassium, and sodium, all those bases are positively charged, so they're attracted to soil. Hydrogen and aluminum also have positive charges, so they're positively charged cations. They're attracted to soil, and they can exchange on and off. That's what cation exchange capacity means. So all the soils can add and exchange cations, but the capacity part of CEC is how much. So not all soils have the same ability to hold nutrients. So down here, the soil would be at some type of equilibrium with potassium that's in the soil water, and there's potassium absorbed, so as the potassium is pulled out, some comes off the exchange. You can exchange things on and off the soil CEC, acids and bases. Base saturation simply is describing how much of your CEC is covered by bases or acids. So older weathered soils should have less bases and more aluminum. Over time, as the soil is leached, these bases leave first, and as it's weathered, it's replaced with acids, so you're not replacing those nutrients or liming it. The soil slowly acidified. Aluminum is held the strongest in soils, followed by calcium, magnesium, potassium, and sodium. So sodium leaches out really easy. So over time, as soils weather, that's why you end up with a lot more aluminum. And that's why things like if you've had, say, tides coming over your soils, they tell you to add gypsum because that calcium's held stronger and pushes the sodium out of the soil if you've had salt water. So when you try to increase your base saturation with lime, you add some type of lime that's adding this base. And it's going to be neutralized by hydrogen or aluminum in the soil water coming off the CEC. So calcium carbonate with water produces calcium 2 hydroxyls. That's your alkaline. And this bicarbonate. So these are going to neutralize the acid, but then acid comes off the exchange, and that's your reserve. If your soil CECs vary, it changes the buffer capacity and how that soil, how much is held in reserve. You can see over here, your CEC on the side, and all these descriptions of different types of soil matter, organic, inorganic, and textures. So obviously, organic matter, we always tell you to add organic matter to soils for water holding and nutrient holding. And it has a high CEC, pure organic matter. So histosols, that's an organic soil. Down here at the bottom, iron and aluminum oxides that coat very old soils have a very low CEC, so they can't hold a lot. So they don't buffer a lot. Textures, loamy sands have a lot lower CEC than a clay. It's something to keep in mind if you're discussing base saturation, that 80% base saturation on a clay versus a sandy loam is not the same amount of total nutrients. So they require still, you might have a soil that's 80% base saturation, but they'll have different lime requirements because it doesn't tell you how much of that acid was held in reserve. 20% acids on a clay is a lot more acids than 20% on the sand. And that's why you got to keep in mind the CEC of the soil. So reserve acidity includes 2 types, exchange and residual. Exchange is mostly what you have to concern yourself with. I just mentioned residual because if you ever discuss soils with someone or you really get into talking about soils like I do, residual is part of the total acidity in the soil, but it doesn't necessarily affect what you want to do to grow crops. So the exchange is what we call the salt replaceable, what they're going to do to test in the lab. Say you add lime, it adds calcium and hydroxyls. Hydroxyls neutralize the acidity. Calcium in exchanges aluminum off the surface. Aluminum splits water and adds more acidity. So that's the reserve acidity. You take care of what was in the soil water, some exchanges off the soil. Residual is more about, let's say, like aluminum that's absorbed to the soil surface. It's in a solid form. So aluminum is part of your acidity, but if it's a solid mineral, it's not necessarily a problem for you growing crops. But it changes with the pH of the soil how it affects your acidity. Same thing with organic matter, and to a degree if you have carbonates in your soil, they can also buffer. Again, we only worry about more about the exchangeable. So a soil like this that has a lot of iron and aluminum oxide coatings, that's the residual. It's there, it's part of the total acidity of the soil, but it's a solid mineral, so it's not really affecting anything. So it can be discussed when talking about how acidic your soil could get, but it's not going to affect you in the crops because the range that we deal with in soils from about 5 to say this is 7.5 or 7.7. That's mainly CEC is dominating your buffer capacity. When you get above a pH of 8, if you've overloaded the soil with carbonates, or you're dealing with limestone, carbonates start to control how well buffered your soil is. You have to get below a pH of 5 before that residual aluminum is really starting to control the buffer capacity. So mainly when we talk about buffer capacity, we can't focus on just CEC for growing crops because that's all that really affects us. So the active, what your crops see, and the exchangeable are the most important thing when considering how much lime to add. Residual is part of it as a soil scientist, but it's not something you have to worry about when talking about total acidity. But if you read soil textbooks and you read about acidity, you might see this mentioned when they talk about total, but it's not really something that you necessarily have to worry about. Something else to consider, if CEC is controlling buffer capacity, you keep in mind that it can vary with pH. So over here on the left, you have whole soil CEC, you have pH on the x-axis, 3 to 8, and your cation exchange capacity going from 0 to about 50. You can see for these 5 different soil types, as you raise the pH, the CEC changes. And the ones that change the most already had a very high CEC, 10 to 25. And usually if you see a CEC that high, it indicates, for the most part, it's organic matter. There are minerals that can do that, but you're not going to have a soil that's purely like a smectite or something. So you already know these soils have a high amount of organic matter, and you see that CEC rapidly changing as you raise the pH. And you look over here at the organic carbon, yeah, clay changes somewhat and increases CEC, but it's really organic matter that increases a lot. So as you change that pH and you raise it, you're actually increasing the amount of nutrients you can hold and increasing the buffer capacity. But if you look at these soils where you really see it happening, a CEC of 10, that's probably a very high amount of organic matter, like 10%, 6%, that we're not really going to see. So it's a factor. If you see your CEC changing or increasing with pH, this could be a reason why. But it's not necessarily you might have to concern yourself with unless you have a lot of organic matter in the soil. How does organic matter contribute to acidity? This is a diagram of what organic matter could look like. It's broken down plant material, insects, microbes in various stages of decay. It's hard to really know what it looks like. It's variable. But this is the diagram that shows you some of the different ways it can look. You see this alcohol on the end here, this COOH. That hydrogen can come on and off the end of that. So as you raise that pH and you add more of those hydroxyls, the OH, it pulls the hydrogen off the end of the organic matter. It makes it negative. The same thing with the edges of clays. So that's why the pH can change CEC, because the hydroxyls pull off this hydrogen. But still, again, it's just something to understand if you have high organic matter soils, but not necessarily something you might see in a sandy soil. So why talk about all these different soils and all these different soil types if you can submit your soil to a lab and get a test back? It's because soils are so variable that you have to understand what test they're running and whether it matches your soil the best, so that when you make that lime application, that you're actually following the amount that you want to need so it doesn't limit you, say, in micronutrients. So a lab is going to do its best to predict regional lime yields, no matter where you send it. They're not going to run 4 or 5 different tests that work on all kinds of soil types because they have to get it efficiently back. So they can do a test that should work for the average in the region. So they're going to consider all the soil factors above, base it on a target soil pH. But your soil might not match those ideal conditions, and that's why you might see a soil under or over applied with lime, even though you follow the exact recommendations. So you'll need kind of what you need in agronomy, period. Being an agronomist, you need good field experience to make sure anything's accurate, whether it's adding nutrients or not. But understanding how the soils can vary and what soil types you might have helps you predict all of this. So what's a basic way to describe how buffer pH is measured? A lot of these buffers that they've come up with, they've tested in labs, they've tested on different soil types, and they've come up with this is how much lime you should add. But just as a basic understanding, say you add soil to the SMP buffer, it's one of the buffers they use, and it's at about a pH of 7.5. Over time, if there's reserve acidity in that soil, that's going to react with that buffer. So you take 2 soil samples, let's say you leave them sit for about 24 hours in the buffer, If the buffer pH is still around 7.4, 7.5, you didn't have a lot of reserve. If it lowers the pH to 6.9, you know you had acidity in reserve. So the lower your buffer pH is, that way you know you have acidity held reserve, not just what's active. Soil tests can tell you other things. You don't have to just look at the pH. All those other things we mentioned about CEC and organic matter. So you have the pH at the top, 5.9. That's your equilibrium. That's what your soils and crops see. So you know whether or not you want to raise it based on that. How much you want to raise it can be based on the buffer pH, 6.9, telling you that yes, there's some reserve acidity. But you can look at that organic matter. 1.3 is kind of low. That tells you, okay, there's probably not a whole lot of reserve acidity. There's not a whole lot of exchange sites. A CEC of 4, still kind of a lower CEC, so you know there's not going to be a whole lot of buffer in this soil. And then you can look at the saturation of acid, 17%. So 83% base saturation. So 17% of the CEC is acidic, and you have a low CEC. So you can look across the soil sample and get a good idea of what your soil looks like and what the factors are to know, besides just looking at the buffer pH, that there's some acidity there, but that you might not have a very large buffer capacity versus something that has a CEC of 10 and organic matter of 6. So a lot of people might, over the years, send their soils to different labs, and some labs might change their methods, and some labs might come and go. So you should always look at what test they're running and make sure you understand what each one does. So there's the SMP buffer, which is meant for soils with high lime requirements but low organic matter content. And by them low, they mean 10%. Obviously 10% would be very high for around here. But those were based out of some Ohio soils that they tested. So it underestimates lime requirement in high organic matter soil. The Adams-Evans buffer is for soils with a low CEC and a low organic matter, so it doesn't have a large buffer capacity. And it's good for extremely small differences. So if you have a soil that doesn't have a large buffer capacity, Adams-Evans can help you find those little increments in change. But it might overestimate when we talk about that pH dependent acidity. And then there's the Malick single buffer, which they came up with because it was good for reducing exchangeable acidity, mainly when they were concerned about aluminum. So the Malick single buffer is good for if you're concerned about aluminum toxicity only. So for areas where they know aluminum's their main problem, they can focus on that buffer. But it might not consider the concentration of micronutrients or the best pH for your crops. So you can see that all these buffers are a little different, and every lab might choose a different one, and they work best for certain types of soils. So if you have a range of soils that you're working with on your farm, you want to make sure how well does it fit this buffer before you go out over or under apply line. So this is from 1996 from an article in a soil testing book. So it's not going to be entirely accurate for how things might have changed, but you can see the SMP, where they use the SMP buffer, where they're going to have lower organic matter but high CEC soils. Adams-Evans, down here in the southeast, where they consider we're going to have older weathered, high humidity area, a lot of leaching, older weathered soils that won't have a high CEC. And then right here in North Carolina, they used that Malick. And then Maryland at a time when they did it, used soil texture as a factor. You can see University of Delaware uses that as well. So this is pulled off of UD's site. You don't have to just go by what's given in the soil test. You can actually go look up these tables for the buffer and look at what the other recommendations would be for certain pHs. So on the left here, you have a water pH, 4.5 to 5.9. At the top, you have a buffer, which I can't read from here, 7 to about, looks like 7.45. And they have a target pH of 6. They're going to have a table for pHs from 5.5 to 6 to 6.5 to 7. So you can calculate how much lime would you need. So if you have a water pH of 5.9, but you want to reach a target pH of 6, and your buffer was 7.75, it's still 7.95. 7.95, they don't recommend any lime until you get a buffer pH of 7.45. But if your water pH was already at 4.5, they start recommending lime when your buffer is only 7.9. So these tables can give you a general idea how much to add, but again, they're based off of tests that were done possibly years ago on soil types. It might not exactly match yours. So even though these are for specific type of soils, they still had to hit an average. Clemson uses the SMP buffer, so this is the table pulled off the Clemson site. Soil buffer pH, the pH you'd like to reach in your soil and how much lime you need to add. Maryland in the past, when they did soil testing, used soil texture. So you can see if you have a clay soil out here, if your pH is 4.5 and you want to reach a pH of 6.5, you have to add a lot more lime to a clay soil than a sand soil, and this may only be attributed to the CDC, that buffer. Because these soils are well buffered, you need a lot more lime to raise that pH in acidic soil. So texture has to be done. The North Carolina Department of Agriculture uses that Malin buffer, and mainly what they're looking at is getting rid of toxic aluminum. So they have the buffer pH and the acidity in the soil and the lime equivalent that is necessary. But they also can use a calculation from the numbers you get off the test to run your lime addition. The exchangeable acidity method determines the amount of lime needed mainly to get rid of aluminum. So their only concern with this is aluminum's toxic to plants. We want to get rid of it. What pH do we need to get to that point? But it doesn't consider if you might have manganese toxicity in the soil, the crop pH needs, the efficacy of pesticides, or even if you're going to lose access to micronutrients by raising the pH too much. Because most lime recommendations these days are meant to raise the pH until aluminum is no longer a problem. When you have an acidic soil, it's not the hydrogen causing an issue. Hydrogen doesn't start to become toxic until, say, about pH of 4 or 4.5. When you get below a pH of 5.5, aluminum minerals start dissolving and releasing aluminum to the soil, and aluminum is toxic to plant roots. So when they recommend a pH of 5.5, right at 5.5, you shouldn't have an issue with aluminum. The problem that people might find in their soils is that if you don't have a lot of aluminum in the first place, a pH 5.5 might get rid of it all, but it also might eliminate whatever micronutrients you had in that soil. So there are some people with sandy soils in this region who won't go above 5.2 because they start seeing manganese deficiency, but they don't have a problem with aluminum. So that's the issue with just basing it off of how much aluminum toxicity is in my soil. You overlook other factors. And aluminum can also be chelated by organic matter. So that's why in a high organic matter soil, you don't need quite as high of a pH because the aluminum chelates or grabs that aluminum and prevents it from being toxic. So if you have high organic matter, it can actually remove some of that aluminum from the soil, and you still, again, don't need quite as high of a pH. And if you raise that pH, you might lose access to micronutrients. So here's an example from Penn State, and only put this up here so you always remember to look, what was the target pH that they were going for? Does it match my crop needs? Does it match how many micronutrients were in my soil? Because when you look at a target pH, the recommendations you should be given are going to be made for a target pH. Make sure it matches your crop needs. And that's why you might want to go back and look at the table, especially if you start to see some issues where it's not matching certain soil types and where you applied it out there. You can also consider what's say the crop response, and this is all Penn State's page, for the different crops. What's recommended for corn can do well between 6 and 7, where soybeans might need 6.5 to 7. But still, that by itself might not be enough if your manganese is low. So you might also want to think past because of the micronutrient availability that varies with pH in your soil. So on the bottom here you have pH, and how wide these are how available the nutrient's going to be to plants. So obviously when you get too low of a pH, when you get below 5.5, you start to see there's that aluminum rising, aluminum toxicity, iron toxicity, manganese toxicity, but they drop off quickly to where they might become unavailable. So the lower the concentration is in your soil, the less likely you are to have some available to your crops. Predicting how many micronutrients are going to be available is tough. It's really easy for us to say if you get above 5.5, aluminum's out. But because micronutrients can vary in their amount in the soil and their availability to crops and what they're absorbed to on the CDC, it's a lot harder to predict. So in general, like with soils, we can do a lot. We might say, okay, if you have a clay soil, you're more likely to have available micronutrients versus a sandy soil. but still it's a generality. The soil variability is a factor. Sandy soils, and I like to use the sandiest ones I can find, they're high in a quartz parent material that are hard to break down. So even if there's micronutrients in there, they're going to release really slowly as that soil weathers. They have a low CEC, so they can't hold many nutrients. So even if you add manganese to it, it's going to leach out a lot easier because there's nothing to hold on to. And it's the same thing with buffer capacity. If you add lime to that soil, the pH can rise very quickly, and it can also leach out quickly, relative to, say, clay soil. So sandy materials, depending on the sand, but in most cases on average, they're going to have a low CEC, low weathering rate, and low micronutrients. Clay soils, higher in CEC in general. Remember, the older they are, if they're covered in aluminum iron oxides, they'll have a lower CEC. But in general, a clay soil can hold more total nutrients, so you're not as likely to see a pH deficiency if you raise it too much. Clays can also weather faster and replace micronutrients. And they're more likely to be seen in soils forming from bedrock. And those soils forming from bedrock, as they weather, are going to release more micronutrients and more sand, silts, and clays as they weather. Coastal clays that we might have, say, in the southern end of Somerset County, depending on what its source was and when it was deposited, remember all these coastal sediments, they're being deposited by rivers, ions like nutrients that are more likely to stay dissolved will probably carry it out to the ocean. And what's left behind might be highly weathered clays and sands that we have here. But it's hard to predict. Just because you have coastal sediment doesn't mean it's low in nutrients. So University of Delaware typically recommends for a sandy soil that you only go to a pH of 6, and a clay they'll say 6.5. Again, this is general. I told you some farmers say on a sandy soil they won't go above 5.2 because they lose manganese. But that's all about the buffer capacity and how many nutrients it can hold and how many nutrients are in the soil. So a sandy soil pH of 6 is safe. pH of clay is 6.5 is okay. This is from Clemson. It gives a really good point about manganese availability in soybeans, how much manganese you need in the soil as your pH changes. So your soil pH here, 5.5, about 4 pounds of manganese per acre is sufficient to grow soybeans. But by the time you get to 6.5, you need about 12 to 13 pounds. So when you look at something like this, you can realize as you raise your pH to try to get rid of acidity, you have to have more total manganese in the soil to make sure enough is going to be available to the plant because it becomes a solid mineral that the plant can't get access to. So it's not just about raising the pH. It's not just about is manganese available or not, but as you increase that pH, the amount of manganese in the soil is important versus aluminum, where we know above 5.5, aluminum is precipitated. That's the chemistry of aluminum. So micronutrients are a lot tougher story. Soil tillage and mixing are also important to keep in mind because if you add lime to a soil that's disc, then you know it's been mixed well. If you add lime to a no-till soil and you add it right before you plant your crop, more than likely, that lime's going to be at the surface reacting, and you'll have stratification of pH, where you have a pH of 7 near the surface, and maybe it drops 6.5, 6, or 5 below. The beginning of growing season, this could be a problem. You can experience micronutrient deficiencies. Over time, as the plant roots get down in this region, they can pick up the micronutrients in the more acidic soil. But it's something to keep in mind if you see something early on in the season. If you have a no-till soil, you obviously want to apply that lime ahead of time enough so it gets down in there and mixes with rainfall. Determining if you have a lime issue in the field can be difficult. This is a field from this past year. It hadn't been limed in about 6 years. They limed it and started seeing some issues. It had several different ideas what were going on, but when you pull some samples, and these are leaf tissues from the soybeans at different rates of decay, I guess. So I took these pictures, sent them around to a bunch of people, said, what do you think it looks like? And everybody comes back manganese. But when you look up deficiencies based on pictures in your crops, manganese or iron, no matter where you look, have very similar descriptions because it's hard to tell the difference between them. They both said, I just copied and pasted that because they both said almost the exact same thing. Interveinal chlorosis on the upper leaves, dark green veins, brown necrosis when severe, occurs in high pH soils. So it's easy to understand we're going to lose micronutrients, but exactly what deficiency you have in that field can be tough to tell. Now around here, it's more likely manganese and iron. Typically have plenty of iron. Even our coastal sediments, they weather from soils and bedrock in Piedmont. It was washed down here, we have iron. From what I've read, it's more of a problem out in the west than it is here. So if you see that deficiency where they look similar, it's probably manganese around here. But you don't want to just assume in soil. That's what I'm saying about just saying, well, pH of 6.5 is okay for clay and 6.0 is good for sand, and doing that the rest of your life. You always want to keep in the back of your mind, well, maybe I should think about this a little further, or maybe it's another issue. These are pictures from all the universities that I can pull, manganese on the left and iron on the right. You can see the deficiencies look very similar in the field. So I took soil samples from this field. This was not a scientific study. This was ag agent trying to help the farmer out and take a look at what was going on. And I did 0 to 2 inches and 2 to 4. And you can see there's a slight difference in pH. It's a little higher 0 to 2 than 2 to 4. But again, I might go out and do a random sample and find it was all the same. And then I looked at all the micronutrients and nutrients at different depths. It was deficient in potassium, so that could obviously be an issue. Low in sulfur and boron, and manganese was low, so the description of the tissue having low manganese makes sense. Copper was high in this soil. When we looked at the plant tissue results, it came up the same, very deficient in potassium. But although the copper was high in the soil, there was plenty of copper, the tissue itself was deficient. Obviously, manganese was low in the soil and was also low in the tissue. So it's hard to see just what's going on. The pH has a large effect on the soil, but there's a lot more going on here than just one micronutrient. And if they'd gotten out there earlier and took a look at the crop after they had applied the lime, they might have discovered something early on. And obviously, they needed to do a soil test period because they were limited potassium. So I had a hard time finding copper deficiency photos because it doesn't come up very often that tissue would be deficient in copper because we have plenty of copper around here. So it does point to, on that end, maybe a pH issue. But copper deficiency it's similar to, looks like potassium in the edge, but it does have necrosis on the leaves. And there was a little bit in some of the leaves I took, but it wasn't obvious just from the sample. But we did know that he had an issue just with too much lime. We just weren't sure, well, next year, what might he have to look for to add to that crop, maybe to the soil or foliar application. And it came up to possibly be copper as well. So the whole point of this discussion is not to make you an expert in pH or go out and do all these measurements and think that hard, but just to understand that soils themselves are variable, which you know that the lime that you might be putting down based on the soil test might not be your best option. And over time, you'll figure that out for certain soils. But you can get a leg up by understanding, well, if you go from a sandy to a clay to an organic soil in certain farms, or if you work in this region over several counties, you'll see that. Make sure you understand when you're talking to a farmer or anybody that you can describe why they might need to add more or less to this soil and why they might need to wash this soil type a little better. Because the lab tests are not equal for all soils. They're the best that we can do in most of this testing. So you want to understand how your soil might not match the average recommendations. Understand that soils have varying amounts of acidity and buffer capacity. And you can simply say, okay, high organic matter, high clay, high buffer capacity. And that lets you know what might be going on. But still, that will vary over time and with application. Scout your fields after you've limed them that year just to make sure. See the nutrient deficient earlier so you can take it on if it's occurring. And if you have to, take a tissue sample so you can know exactly what the problem was and maybe address it next year. And give that lime plenty of time to react before planting.